Let's go into a little bit more detail now about OSPF by looking at the different kinds of OSPF packets, what they're used for, and their purpose. So like EIGRP, how EIGRP had specific packets to do certain things like the hello, the update, the query, and the reply, OSPF also has specific packet types. We have the OSPF hello, and just like you could guess, that's used to dynamically discover OSPF neighbors and to maintain OSPF neighbor relationships, what we call adjacencies. Then we also have these other packets which are used in the process of building a neighbor relationship, the database descriptor and the link state request. So the database descriptor and the link state request, you will only see those when a neighbor relationship is very first being built. After that neighbor relationship is up and maintained, you won't see those again. And then you also have the link state update and the link state acknowledgement packet. And the vast majority of those are sent as multicast. So I'm going to come back to those in just a moment to talk about how they're used and during what process they're used. We will get to that. So just like with EIGRP, how there were certain things during the hello packet exchange that had to match with EIGRP, here you can see there are also certain things that need to match for an OSPF adjacency to fully form. So number one, the timers, the hello and the dead interval, they have to match. This is different than EIGRP. In EIGRP, we could exchange hello packets, and my hello packet to you might say, hey, if you don't hear from me within 5 minutes, declare me to be dead. And your hello packet to me might be, hey Keith, if you don't hear from me within 30 seconds, declare me to be dead. That would be fine. As long as we set our expectations appropriately, we'd be okay. With OSPF, those timers have to be the same. Authentication, which, as I mentioned in an earlier video, is optional, but if you are doing authentication, the type of authentication has to be the same, because you and I could either exchange clear text passwords, or we could exchange passwords that are hashed with the message digest formula. So the type has to be the same, and clearly whatever the password is has to be the same as well. The area ID. So you and I share this common link, this common cable. If in my network statement that covers this cable, I believe this is an area 1, you also need to believe this is an area 1. If I get a hello packet from you indicating that you think this link is an area 50 and I think it's an area 1, that's going to be a problem. We will not form a neighbor relationship in that case. The prefix length. So this is also a little bit different than EIGRP. So in EIGRP, let's say I sent you an EIGRP hello packet, and let's say it was like this. So here comes in an EIGRP hello packet, EIGRP hello, and let's say the source of that packet was 1.1.1.1. Okay, that was the source IP address. And the router that's receiving that packet on this interface, his address is 1.1.1.9/29. Would he say this source is in the same network as himself? Hopefully your answer was no, because 1.1.1.9, that's a host address. Because if we're doing the /29, that means this is a host in the 1118 network. 1118 and 1119 is the very first host address, and 1111, that's not in the same network. So this router here, router X, would say, neighbor not on common subnet. I'm receiving EIGRP hello, but the neighbor's not on the common subnet. But what about over here? What about router Z? What if his address was 1111, because that's the source he's using, /24, and here he receives a hello packet sourced from 1119. Is router Z going to have a problem with that? No. Router Z is going to say, oh, well, I'm in the 111 network. This source is also in the 111 network. So he looks good. So now we're going to have a problem here because router Z is going to say, hey, router X, you look good. We're good to go. Router X is going to say, I can't talk to you. You're not on the same subnet as me. So only router X was able to figure out this was a problem. Router Z did not know this is a problem. In OSPF, this would be a problem for both sides because in their hello packets, they actually include what their subnet mask is. And both sides would see that the other side had a different subnet mask. Router Z would say, wait a second, you're telling me your subnet mask is a /29. That doesn't match me. I'm a /24. And so in OSPF, that's why we say the prefix length has to be the same. So it's a bit better at discovering these types of problems than EIGRP is. And then the last thing that has to be the same is something called a stub area flag. You don't really get into that in the world of CCNA, but a stub area is basically an area, a collection of routers where there's only one way in and one way out. There's just one area border router, and that's the only way out of the area and the only way into the area. In that particular case, you can take all the routers in that area and configure a special command on there saying you are all part of a stub area. And the actual benefit of that is that area will not have to learn about everything. You can reduce the size of the OSPF tables when it's a stub area. But if you do that, all the routers, when they're exchanging their hellos, have to have a little flag raised saying, I believe this area is a stub area. They have to agree on that. Okay, so let's go back to these different types of OSPF packets and how they're used. So the first thing, step number one, is we have to exchange hello packets. And those things that we saw in the previous slide have to match. So let's say that that is the case. So you and I exchange hello packets. So inside the hello packet, if I was actually to draw a hello packet, so let's say here's a hello packet, there's a field in here where you list neighbors. Which means when I send you a hello packet, I'm telling you, here's all the neighbors I know about on this link. On this link that you and I share, here's all the neighbors. Now you might be saying, well, wait a second, it's just you and me, right? Why do that? Well, because there might be more than one neighbor. Imagine this link was connected to a switch or a hub in between us, and there were 5 or 6 routers all on the same VLAN, all on the same subnet. Well, my hello packet would list all the routers that I know about that I'm neighbors with on this link. So what does that have to do with this? Well, when you type the command show IP OSPF neighbor, show IP OSPF neighbor, you'll see if you've got any neighbors and what state you're in. You see in EIGRP, it's pretty much all or nothing. When you did show IP EIGRP neighbor, you either saw a neighbor or you didn't. There was like no intermediate steps. But in OSPF, there are, and you need to know what those steps are in building a neighbor relationship. So step number one, here comes in a hello, and router 1 is getting that hello, and the hello says it's coming from router 2. But in the hello packet itself, router 1 says, okay, I see there's a router 2 here on this link. He and I match, everything looks good, but he doesn't recognize me. In other words, in his hello packet, I don't see my own name, so I don't even know if he's gotten my hello yet. All I know is that he exists. So in this way, router 2 would be in what's called the two-way, in the init state. Init, or the initial, it's called the initial state. So if you did show IP OSPF neighbor on router 1, you'd see a neighbor of R2 and the state would be init, meaning initial. I've received his initial hello, but I don't know if he even is aware of me yet. Now let's say a hello comes in from router 2. And it says, I see R1. So now my neighbor relationship would change to what's called the two-way state. Router 1 would say, okay, I see him and he sees me. He's actually got my name, my router ID, inside of his hello packet. So that means he must have received my hello packet. We see each other. Now we're at the two-way state. So at this point, now the routers recognize each other and things have matched. Now it's time to progress to the next level. Now the next step is you and I, router 1 and router 2, we have to say, what's your LSA database look like? Do you have the same LSAs as me? Because if you don't, we need to synchronize. So that's going to be the next step. So you might want to, I'm about to erase these right here. So you might want to write these down before I do. Let's see here. Maybe I can fit a little bit more on this screen before I erase it. Okay, so the next thing is router 1 and router 2 will both send each other another type of OSPF packet that we looked at real briefly called a database descriptor. So the primary purpose of exchanging these database descriptors is to determine, does your LSA database look like mine? And these are going to be exchanged back and forth. They give sort of like a view of what my database looks like, what your database looks like. And so now, as we're exchanging database descriptors, we're going to move through two additional states. We're going to move through the EX start state and the exchange state. Exchange. Sorry for my sloppy handwriting here. So we started out at init, then we went into two-way, and remember, if I'm doing show IP OSPF data, show IP OSPF neighbor, I'm going to see these various states in the output if I keep doing that command over and over again. So exstart and exchange means we're exchanging these database descriptors, trying to discover if our databases are the same or not. And they probably will not be the same. So now I have to erase some stuff to make some room. So after the database descriptors are exchanged, and we discover that we're missing some stuff, that your database is not the same as mine, then at that point, I'm going to say, okay, you've got some hello packets, you've got some link state advertisements that I don't have. I would like to have them. And so each router might send each other link state request packets saying, hey, you've got a link state advertisement I don't have, please give it to me. And that will be followed by a link state update packet. So now they're in the process of actually making their databases in sync, synchronized by you send me some requests of what you don't have, I send you back some updates. I send you some requests of what I don't have, you send me back some updates. So now we're going to move into a different state, which is the loading state. So if you issue the command show IP OSPF neighbor and it says loading, that's what's going on. They're requesting LSAs and updating each other with LSAs. And then finally, we're going to eventually reach a point where we realize, hey, we're the same. My database has exactly the same stuff as your database. Now all we have to do is go back to exchanging periodic hello packets, and that's it. And now you'll finally be in what's called the full state, which means we are fully adjacent. We are fully loaded. Everything is fully synchronized. So that's the series of steps that two routers or two OSPF devices will move through to finally become fully adjacent. Init, two-way, EX start, exchange, loading, and full. And so now we've talked about where those various packet types are used in the process of building an OSPF relationship.